Hey, I'm back for another video. So I'm going to be talking today about a video I've been promising to do for a while, which is about the multivariable Taylor expansion. So the multivariable Taylor expansion is used in a couple of places in the course. It's used in the derivation of the divergence of a vector field, and it's also used in the derivation of the curl of a vector field. So I wanted to just go through that derivation. This derivation is not, strictly speaking, part of this course, although we use some of the results. It is something that you're going to look at in other modules coming up. So it's really important that you've covered this and have an idea of what this is for those other courses. But it's not something which is examinable, but it's really, really important that you see this. So let's start this. So we're going to do multivariable Taylor series. Multivariable Taylor series. Okay, then what we're going to do this is we're going to construct our multivariable Taylor series out of the one-dimensional Taylor series which we're familiar with. Okay, so we're going to start with let f, so R is some vector, and since this vector is going to be multi-valued, right? So this is our multivariable scalar function. So let f of R be some scalar field. We know that if I take the dot product of some vector A with the gradient of f, what that is, this is called the directional derivative, right? So we covered this in the course. So if you're not sure what the directional derivative is, just go look that up in the right section of the notes, and we did this in lectures. So this is the directional derivative. This is the directional derivative of f in the direction of A. So in other words, this tells you the slope of the scalar field in the direction of A. Okie doke. Okay, so let's write that more explicitly. If I want to write down the directional derivative explicitly in terms of this kind of standard ways in which we derive differentiation, I want to write it as limit of some gradient. So I'll rewrite this as the following. So this is the limit as epsilon goes to 0 of f, and we're going to start at some just general point. Remember, our general point is R, so starting at some general point, and we're going to move epsilon in the A direction, so a small amount in the A direction, and we're going to subtract from this our original position, and then we take the slope of this function. Okay, so this is the slope in the A direction, moving some small epsilon in that direction. Okay, so what we want to do is we want to work out exactly what this is. So we're going to consider just part of this. Okay, so we're going to look at part of this expression. Specifically, we're going to look at this first term here. Okay, so this is the first term we're going to look at in a bit more detail. So for that, we're going to define a new function. So it's a new scalar field. Except it's going to be a function of just one variable, right? So we're going to define a new function, and it's a function of one variable, and we're just going to define this to be our f function from before, but we're going to evaluate it at a particular point, right? So this was general, R was in general, but now I'm going to evaluate it at a particular value of R. this a vector was already a particular vector, right? It was in a particular direction. So this is a constant and this is a constant. These don't vary. And the only thing which varies is the value of epsilon. Okay, so I'm going to define this to be my function psi of epsilon. Okay, so since this is a 1D function, one-dimensional, I can use the one-dimensional Taylor series on this, just a standard Taylor series expansion acting on this. So I'm going to take the 1D Taylor series of this. Okay, so what does that give me? So the 1D Taylor series of this function is going to be, so let's say we have to choose some point we're evaluating. Whenever we do a Taylor series, we have to center our Taylor series at a particular point. So I'm going to center my Taylor series at the point 0, right? So I'm going to set this to start off at 0. So that will be, just going to look at the first 3 terms. Okay, so from standard Taylor series, we know this is the following. Okay, so that's just how you do normal Taylor series, then you have higher order terms. Okay, dot dot dot. Okay, so that's how we expand this function as a Taylor series. Well, how do I write down these derivatives? Right, I've got my definition of psi up here, and I want to write down these derivatives more explicitly. So I'm going to write down these derivatives in terms of the right-hand side of this definition. So let's take the first derivative first. So I'm going to say this, go back to my standard limit definition of the differential. So the limit is epsilon tends to 0 of this evaluated at a particular point. So this will be f divided by epsilon. Okay. So as epsilon tends to 0, this will be the case. And I can rewrite this in a slightly different form, because now I know that this is basically like my definition up here, right? So my definition of the directional derivative and this expression here are basically identical. The only difference is I'm evaluating this at a particular point, r0, and this was completely general. So I can rewrite this as a dot the gradient of f, but now I'm going to evaluate it at the point r equals r0. Okay, and that's it. That's all I'm going to say. I'm going to say the first derivative of this is equal to this, evaluated at a particular point. Okay, similarly for the higher derivatives. So higher derivatives are the same. Okay, so I'd do exactly the same procedure, just doing the limit definition of the second derivative. So I just take the derivative of this, and we've covered that in kind of just normal linear analysis. So that's pretty straightforward. So I can put these expressions into this Taylor series. So that's what I'm going to do. I'm going to replace these expressions with these sorts of expressions. And that will allow me to write down this Taylor series in terms of f now. Okay, so I had a Taylor series for this, and this was defined to be the following. And now I can just fill in the Taylor series for this expression. So this is going to be this term plus a directional derivative term evaluated at some point, and this is multiplied by epsilon. And then I'll have another term. And it just so happens when you work out the higher order terms, it comes out the following way. Now I'm going to explain this notation more explicitly a bit later. So this notation might not be familiar to you, but I'll write this out more clearly momentarily. And then we have higher order terms. Okay, so I basically constructed a Taylor series of this function, and I've now input into that Taylor series the explicit definitions in terms of f of each of those components, and I worked out that the first derivative of psi is actually this directional derivative evaluated at a particular point, and the second derivative is actually this evaluated at that same point, and then there are higher order terms which follow in the same way. Okay, so if this is correct, what I can do is I'm going to set epsilon to equal 1. Right, so I can set epsilon to be whatever I like. I'm just going to happen to set it to equal to 1. And I'm also going to set my general directional vector A. I'm going to call this, again, I'm free to set this to be whatever I like. I'm going to set it to be the following. I'm going to call it this vector. And I'm going to set R0 to be this vector. Okay, these are all things which I'm free to choose, and I'm going to choose this particular form. The reason I'm going to choose this particular form is that it simplifies a lot of what's happening over here. So let me write down this in terms of these expressions now. Okay, so what happens? I can do this as the following. So over here I had R0 plus A times epsilon. So if epsilon is equal to 1, this just becomes R0 plus A. This is what I'm setting R0, this is A. So if I add these two vectors together, what do I get? I just get the vector xy. So this is f of x, y. Okay, so just acting at that particular general location. What does this equal? This equals f as a particular point, and I'm free to choose x0 and y0 to be whatever I like. Just like you do in 1D Taylor series, like you set a particular center point for your Taylor series to expand around. That's what this is. It's the two-dimensional equivalent of that. Then I have this term, this directional derivative term. Okay, so I'm going to do the a dot the gradient of f. So what does that give me? So I know what the gradient of f is, and I know what a is. A is this. So what I find is that this is actually going to give me two terms. Remember, this is a dot product. So a dot product is exactly what it sounds like. So I take the gradient of this and I dot it with a. So I'm going to get one term from one component of the vector and another term from the other component of the vector. So if I write this more explicitly, I will get the following. I'll get the derivative of f with respect to x at x0, y0 multiplied by the first component of a, and the next term will be similar but with the y version. Like that. Okay, so that these two terms correspond to this term here. Okay, what is this notation more explicitly? So if I write this more explicitly, you'll understand what this notation means now. Okay, so more explicitly I'm going to write this. This is 1 over 2 factorial multiplied by, so the first term is the second derivative of f with respect to x squared evaluated at x0, y0, and it's multiplied by x minus x0 squared. Then I have plus 2 second derivative of f with respect to x and y evaluated at a particular point, x0, y0, and this is multiplied by x minus x0, y minus y0. And the last term is the second derivative of f with respect to y squared evaluated at x0, y0, multiplied by y0, y minus y0, all squared. Okay, so this is explicitly what this notation means. So this notation actually just means this. Okay, and then there'll be higher order terms following the same pattern. Okay, so we've got the first three terms. So we've got the linear terms, sorry, we've got the constant terms, we've got 2 linear terms, and we have 3 quadratic terms. And you just follow that same pattern and you can build up the whole Taylor series. And that's it really. So that's how this is the main expression. So this expression here is the multivariable Taylor series expansion. Okay, so this is the important result. Okay, so how did we use this? Okay, so bear this in mind. So we use this in the following way. Okay, in the derivation of the divergence of a field and the curl of a field. So in the derivation of the divergence of a field and the curl of a field, we found the following. So we were trying to use the following result. So we had the x component of the vector field evaluated at a particular location. It was evaluated at x0 plus delta x over 2, y0, z0. Okay, so what we wanted to do is a multivariable Taylor expansion of this quantity. Okay, so what will this be? Okay, so first of all we're going to have to choose our center. So we're going to choose for our center x0, y0, z0, just because it leads to nice cancellations. Okay, so going back to here, okay, this is the 2D case, but we can do a similar thing for 3 dimensions as well. For 3 dimensions, we'll simply have an extra term here, which is a z version of what we've had for x and y here. Okay, so if I choose to center my expansion around x0, y0, z0, then the first term in this expansion has to be just x0, y0, z0. Okay, that's the constant term evaluated at a particular point. Then what will I have? I'll have the derivative of this with respect to x also evaluated at x0, y0, z0. Okay, I'm going to put brackets around this just to make it clearer. And then this is multiplied by, so if we go back to our Taylor series expansion, it's multiplied by x minus x0, where this x is the point at which we choose to evaluate it. If I choose to evaluate this at x0, y0, then this term will cancel. Okay, so whatever appears here is what this x, this y is. These x0s are independent of what appears over here. I'm just choosing, in this case, that these x0s are also where I'm centering my derivation. So I would have here this term, x0 plus delta x over 2 minus x0. Okay, so compare this to what we have on this page. I have here x minus x0 is coming from a point at which I choose to evaluate it. Here I have my x is defined to be this quantity here, and I subtract off x0. Okay, then I'm going to have a similar thing for y. And here I'll have y0 minus y0. And I'll have a similar thing for z. Oh, this shouldn't say y here. That should have been an x. Partially differentiate, oh, that should be a z. Oh gosh. Okay. So the x component of the vector field partially differentiate with respect to z. And then I'll have z0 minus z0. And then I have higher order terms which I'm not interested in. I'm only interested in the first linear approximation. Okay, why am I only interested in the linear approximation? Well, in this derivation for the curl and the divergence, I'm taking the limit as these things become extremely small, so I'm only interested in linear limit. That's always what we do whenever we do calculus. We try and approximate things to a linear regime, even if they're not actually linear. Okay, so as you can see, this term will go to 0, this term will go to 0, and the only term I'm left with is this one. This becomes just delta x over 2. So in the end, up to linear order, this is simply plus higher order terms. Okay, and this was the result which we then used in both the derivation of the divergence and the curl. Okay, so this was the key result. So that explains then how we came up with this result, and that's how you do multivariable Taylor series expansions. I want to do one other quick example, just so that it's absolutely explicit how we do multivariable Taylor series. Okay, so this example is somewhat simpler. Okay, so we're going to expand this particular function in a Taylor series about the point xy equals 1, 1 up to quadratic terms. Okay, so let's write down the Taylor series formula. So I have my function f(x,y), and this equals the following. So this is the constant term, this is the two linear terms, then I have my quadratic terms, so the first of the quadratic terms is just 1 over 2 factorial times this. The middle actually is multiplied by 2, so I get 2 of these. And this is the second differential of x and y. Okay, I pick up 2 of those. So this 2 will actually cancel with this one. This is also evaluated at x0, y0. And this is multiplied by xy. And the last term of the quadratic cases is this. And then we have higher order terms. Okay, so that's the Taylor series expansion. Now I just want to evaluate this at the point 1, 1. Okie doke. So, so what I'll do then is I need to work out each of these quantities. So let's work these out first of all. So I have f of xy, that just equals, well, I'm told that in my expression, in the question, that equals this. So if I evaluate this at the point 1, 1, what do I get? I stick in my numbers and I get 27. Okay, let's do the same thing for the partial differential with respect to x. So for this, I'll have bring the power to the front, differentiate what's inside the brackets, reduce the power by 1, and I'm going to evaluate this at the point 1, 1, and I get 27 again. Now I do the same with respect to y. Here I'm going to have 6 times x plus 2y. And I evaluate this at the point 1, 1. And I get 54. And now I can move on to the second derivatives. So I'll have d2f by dx squared. So I'm differentiating this expression with respect to x. So I'll have, oh, sorry, this should have been a squared here. I missed that out. Okay, so I'm differentiating this expression with respect to x. So I'll pick up a 6 x plus 2y, and I evaluate this at the point 1, 1 d2f by dx squared 1, 1, and I believe I get 18. And if I take the mixed derivative term, So I'm either differentiating this one with respect to x or this one with respect to y. It makes no difference which one I do. Okay, so let's take this one for example and differentiate this with respect to y. So I bring the power to the front, that becomes 6. Differentiate what's inside the brackets, that picks up another 2, so that becomes 12. So I have a 12 on the outside, x plus 2y. Now I'm going to evaluate this at a particular location, at 1, 1, and I get 36. And the last term I'm interested in is the double derivative with respect to y. So this will be given by, let me see, so I differentiate this with respect to y, so I should get 24 x plus 2y. And now I evaluate this at a particular location, and I should get 72. Okay, great. So now I have all of these numbers. I can just stick those into this expression, and then I'm done. I just need to be careful and make sure that this one will cancel, and these ones are divided by 2. So this is divided by 2, this is divided by 2. Since 2 factorial is 2. So long as I make sure that these coefficients are taken care of, I just stick in all of these numbers into here. Okay, so what do I get? Go to a clean page. So in the end, I'll find f of xy equals 27 plus 27x plus 54y plus 9x squared plus 36y squared plus 36xy. Okay, that's it. So that is the Taylor series up to quadratic terms for that particular function. So there are higher order terms. Okay, so I want you now to try yourselves e to the x plus 2y. Okay, so imagine this is your function. Okay, I want you to try that yourselves. Give that a go. Just make sure you're familiar with how the multivariable Taylor series expansions work, and that will give you a good grounding for what you'll cover in, particularly in Mark Dennis's course, who I promised that I would cover this in lectures and I just didn't get time to do. So when you do this in Mark Dennis's course, hopefully you'll now have an idea of what he's talking about. Okay, let me know if anything of that is unclear, if there's something you want me to go over, but hopefully that's nice and simple. Okay, thanks very much.